at the end of last time I said we were going on a linear regression, but there's one more topic in analysis variance, and that's random effects. That instead of being interested in every single group, groups are really ones that we're interested in, sometimes groups represent a sample from a population. And then instead of being interested in every one of those groups as an individual group worthy of inference and estimating the means, we're really interested in the variability among them out of a population. So it's called random effects because there's instead of a fixed effect for each of those groups, there's random effects that generate the population. It's like a random sample of groups. So in the usual analysis of variance model, which is called fixed effects, which we've been doing so far, we could write it as the mu sub ij is a mean plus some error as a model. And these epsilon ij's are given some normal distribution with a constant variance, so that the way the groups differ is they have different means. And that's what we've been essentially using as this kind of idealized model, where the mu i's are fixed effects, they're the effect for that group, and the difference is there. And that could be written differently. It could be written as a mean plus an effect. And to make that identifiable, that we can distinguish what these things mean, in the fixed effects we make an assumption that across all the groups that these deviations add up to 0. So the average of the means of these across the groups is just the population mean mu. Right? So this says that the expected value of a Yij term is mu sub I, which can be written as mu, the overall mean plus this deviation, and the variance of each of these observations is within a group is just sigma squared. Right? That's what we've done, and we've done the F-test to test whether these mu sub i's, or equivalently whether the AI's are different from each other. Right? In this case, when we test and think about it, mu i's we're testing, are they different from one another or not? When you focus the test and think about it in terms of the AI's, you're asking, are all these deviations 0 or not? Right? Because if they're all 0, then the mean for every group is the mu. Right? But in some cases, there are many groups, and the groups, or maybe there's just a few, but the groups represent a sample from the possible groups. Right? And this number of groups, the capital I, is not necessarily exactly fixed in the population. You could have sampled more groups, taken more cases there. Right? So if the groups themselves they're sampled from a large population of groups, or sometimes just if there's many groups that are being compared, we might think about things different. There are many groups in the sample. We might, view the group effects as random instead of a fixed effect for that group. That we're sampling from a population and we get some effects. View the group effects as random. So in the analysis of variance random effects model, we're going to write outcome y sub ij as the overall mean, but we're going to put an alpha I here and then an epsilon ij. This is an I and j subscript here. And so instead of an A, a fixed effect for that group, it's given this alpha, and we're going to think both about the errors, the deviations or residuals within the group as having distributions. And put a little epsilon here because that's the error for that one. But then the alpha i's are going to be normally distributed with some variance. So as you sample groups, you get a new group effect, and then you sample individuals within the group effect, within that group, and you get some other deviations. So there's kind of two sources of randomness. Which groups do you pick, and which one's there? And they're both viewed random. And so one thing this is done, particularly if you have many groups, instead of having all those separate AIs that have to add up to 0, right? I minus 1 independent deviations, right? They're all essentially governed by one parameter in this normal distribution now. So instead of having, if you have 25 groups, having 25 different parameters you're estimating with their means, effectively the thing you can be interested in is just what's the magnitude of that variance. Right? And so there becomes a great economy in describing something like that. And in other cases, there's just the context where the groups are, just a random selection of possible ones you might have looked at, so it fits that hypothesis. Right? So there's a few things we can look at with this. This one has both a mean and a variance, an average response and a variance of a response within the subjects in that group, but then also overall, total variability, or the overall average that we can look at. So under this model, the Yij is the mean plus the alpha i's plus the epsilon ij's. The expected value for Yij in the group i's, right, conditional on the fact that it's in group I, is going to be the expected value of this mu plus the epsilon I plus this thing in group I. Well, in group I, the mean that's the population mean, and this is the effect in that group, so it's not random within that group once you've chosen from that group. So the expected value is modified by whatever the expected value of this error is. And the errors just have 0 expectation. So the conditional expectation, we can think about the random variable within that group. But you can also think about the expectation of it overall. And from probability theory, there's an expectation of a conditional expectation formula that really can be used here. And the expectation inside of a group is mu plus alpha I. But the average of these random deviations is also 0, so across all the possible groups. So it just ends up being mu plus the expectation of this. The distribution of those is 0 here. So on average, our y's are centered at the global mean. Well, conditional on a group, it's group mean. Is one thing you get out of that. So you can also think about that in terms of variance. There's a conditional variance. Within each group, there's a sigma squared variance. Then there's a variance of the measurements overall, right, across all the groups. Right? And so we have this model. So the variance of the y sub I j's in group I Well, that's just the sigma squared for this one, right? That there is, right, once you're in a group I, the variability is just governed by that error variance, right? The variance overall of an observation, though, ends up being the sum of the two variances. How variable are the groups, and then how variable are the individuals within the group, right? Then those two things, if they're independent, they're added together, the variance is added. All right, so we get this, these two, the total variance is related to the spread of the groups and this. Then we can look at something called covariance. The covariance between an observation, two observations that are in the same group. Is the covariance, there's a mu plus alpha I plus the sigma ij, and there's a mu plus alpha I plus sigma ij prime. We're not going to go through the probability theory, but it really comes down to, you know, the covariance of these two terms, which is the variance of the alpha i's. And so that just ends up being, right, the sigma squared for the alpha. A covariance between two observations in the same group. So if you have two observations randomly selected and they're in the same group, well, the model, you know, would generate them independently, but because they're in the same group, they have a similar group average, and so they're somewhat related to one another. If there is some variability there, if you have two observations in different groups, then there's no covariance between those two. So there's a little I prime, J prime here. Different groups, I is not equal, it ends up being 0, but there's no reason that they should be associated with one another. The alpha I and an alpha I prime should be, you know, there's no correlation of those. It's independent. Those effects are generated independently. So the correlation, or the COR, between two observations in the same group, so two in the same group, is going to be the ratio of the covariance, which is a sigma squared, the square, sigma squared alpha, right, divided by the square root of each of the variances. And the variances are the same, and so you take the square root of one times the square root of the other, and so you get the sigma squared alpha plus sigma squared epsilon. Oops. So there is this ratio here, right? And this is called the interclass correlation coefficient. And I'll write that on the next page. But it's kind of a measurement of how the observations are associated with the groups, right? And if there's big group differences, then you're going to get a large correlation here. And if there's almost no correlation, and this variance is rather small, you're going to get small values of that. Yes?
Just to clarify, the alpha next to the sigma square, that's a subscript, right? In
Yep.
this case, okay.
Yep. These are, subscripts. I can be a little bit closer. Over there. So in this random effect, so the ICC intra-class correlation. This thing we think of as being, it's between -1 and 1, but almost in all cases we would tend to think of it as being positive. And this ICC is the sigma squared of the under the alphas, the sigma squared under the epsilon, and so it becomes some measure of how associated these things are. So when we do our tests, so things that you can do with this random effects, you can do the same analysis of variance f-test for testing whether there is an effect of the groups being different. You can still do that. But then you could also, in some applications, look at this correlation coefficient or these separate variances to get other measurements of things, right? So it looks a little bit different in some of the output, but you can really do a few different things by looking at the random effects, looking at the group effects, and producing different types of intervals a little bit. So we'll look at just a little bit of that and then look at some numerical examples, right? The random effects will come back as we go through the course, a little bit in regression, some with two-way analysis of variance and so on. So we'll get kind of an introduction to it today and then look at some output that comes out of that, right? So if we wanted to test, we had a null hypothesis of no group effects, right? So our groups don't make any difference. This is going to be translated into a test of whether the sigma squared of alpha equals 0 versus an alternative that the sigma squared alpha does not equal 0. If the sigma squared alpha equals 0, right, then alpha I is going to be 0 for all I, and the average in group I, which is the overall mean plus the alpha I, is just going to be constant, the overall mu. This test is basically equivalent to testing the means from before. Right, so we're going to calculate our F statistic as before, the mean square for groups over the mean square error. Right? And we're going to compare that to an F distribution with our I minus 1 degrees of freedom, 1 less than the number of groups, and the N minus I, which is the total number of observations minus that, and we're going to reject this null hypothesis that there's no group effect if we get the same ANOVA result. So the significance isn't going to be changed appreciably by that. And we can do confidence intervals for an individual mean. Right? But the one example of something that we can do different is you can look at that interclass correlation coefficient or the variances themselves and do confidence interval for different variances. So for instance, if you're interested in this interclass correlation coefficient, sigma squared alpha plus sigma squared epsilon, right? The F statistic, right, had a well, let's see, instead of what I want to say, that's why that's there, right? So under the model, right, the expectation of the mean square error ends up being sigma squared for this, right? And the expectation of the mean square group under the model, let's assume just for that there's some constant sample size per group. You can do different things if it's different. But the expectation of the mean square group is this one plus the number per sample size times this one. So there's a little bit of the mean square group has this extra piece in its expectation, right? That's there. And so the F statistic, so kind of a modified F statistic, you take the mean square groups divided by its expectation, sigma squared epsilon plus this thing over the mean square error. It's not really a statistic anymore, so let's erase this statistic thing. And it's different from the other one. So just to make sure that we know that it's different, I'll call it F star, just to clarify that it is in fact a different thing. Oops, this should be the little epsilon. The mean square group divided by its expectation, and the mean square error divided by its expectation, under the model still has an F distribution with the, now it's going to be I times n sub 0 minus 1, because we assume this constant number. We still have this F distribution. Under the null hypothesis, when we did the hypothesis testing, we assumed that this was 0, so these two things would cancel. The old F statistic under the null hypothesis just was the ratio of those two. But with this, you can set up an interval, the probability that this thing is between the 2.5% lower cutoff on the upper 2.5% cutoff. Right? Under that distribution is going to be 95%. So we can write something that the probability that, let's say we'll call this a lower value here, is less than the F star, is less than an upper value at 95%, where our F star is that thing. And this lower value is going to be the F distribution with this number of groups times n sub 0 minus 1, the 0.025 level, right? That's the lower one. And then the upper one, this is the number, letter L, is going to be the F distribution value at the 0.975. So we're taking this F distribution picture and choosing the two cutoff values to give us the F lower and F upper. And we can do some manipulations of this thing to change it around so that we get an interval like this, but with our interclass correlation coefficient in the middle. But we can change around this probability statement with some algebra and get something that gives us two limits, and we can use that as a confidence interval for the interclass correlation. Right? It's a little messy, manipulating all those around, switching from something like this to the other one, but it works out. Right? So you can manipulate all that around and get a probability that a lower interval is less than or equal to a ratio of variances is less than or equal to an upper one is 95%, and that lower value there, the lower value with some manipulation is 1 over n sub 0. The ratio of mean square groups to mean square error, 1 over the upper F value from before, and all of that minus 1 on the upper value equals 1 over n sub 0, number per group. It's not, that's just a bracket. A bracket, the same thing, mean square group, so we're mean square 1 over the lower one minus 1. So if we calculate that, these are the F distribution values from the probability distribution. These are mean square groups and mean squared error we compute n sub 0 observations per group. And we get an interval for this ratio of variances. And we can convert that into a, I call it L star, less than or equal to R sigma squared alpha plus sigma squared E. That's 0.95. And these, the L star ends up being L over 1 plus L, and the U star ends up being 1 over 1 plus U. Because if you take, right, let's see, if you take 1 over 1 plus sigma squared alpha over sigma squared epsilon over sigma squared, which one is that? Sigma squared. That, and you multiply all the way through, you get this, sigma squared U over sigma squared epsilon plus sigma squared epsilon. So, kind of doing, if you had this and wanted to get to this, the function that does that is 1 over 1 plus the thing. And so if you apply that to the endpoints, it transforms it the same way, and you get intervals. So anyway, whatever you would calculate for those ends up being a confidence interval for that variance, right? So you can do a lot of the same things, but viewed as random effects, you get a little bit more. You can test the same things and look at these things. The aspect of it is it uses fewer parameters, so it can be a little more, a little bit better in terms of fitting and testing by not using. But anyway, maybe that doesn't come through in this, but we'll look at some examples and see how it gets implemented in those. So that's kind of, the book doesn't present as much theory, right, in terms of how this would go. But another book that would have more of the mathematics, a linear models book or analysis of variance book, likely would go through some of more of these distribution things and present something like that. But let's look at an example, right? So on the handout in R, we're going to return to this, for now, this the two data sets that are in the chapter 5 in terms of the trials and the diets. So first for the lifetime diet one, I guess primarily I'll just read off this effect here. So fitting analysis of variance, one of the two ways. This is what we did before. It gives us an analysis variance table, and you see that there's a very large F statistic, and so there's a very big difference between the average response in terms of lifetime of these different diets, right? The way that the random effects analysis gets done is with a different command, and LMER, so linear mixed effects, random effects model, linear model estimation with random effects, I think is how it comes about, this acronym, LMER. that's a package that's in a package called LME4. So you have to install that package and you put it in the library to have it operate, right? And so for you, when you're doing it, or when I'm doing it on my computer in my office, I would go under this install button and LME4 and click it, and it would install. And I don't want to put it to the desktop there because it doesn't like to write there. So I would do something like this to put it in my R directory there. I'm not going to do that right now because I always fear that it will hang up or do something funny. But when I would do that, then the specification is changed a little bit from the linear models command. A lifetime is still the outcome. There's a tilde, right? And then these are the things that it's distributed as. And the way the groups are specified is with a parentheses, a 1, and then a vertical line, and then diet. And this will have constant, so effects that don't depend on any covariance or any other variables. They're not scaled in any way, but they're defined in terms of the diet categories, right? And so you'll get like that, right? So in this, fitting this model, there's a couple ways to do estimation. One is called restricted maximum likelihood, where basically they estimate the variances, and then conditional on those, they estimate the random effects, right? So that's one way to do it. Or you can estimation with maximum likelihood. That they write out the probability density function and jointly maximize for all the parameters. It's a little more computationally intense, so the default is to do this restricted maximum likelihood, which is a little quicker. Would be easier if it's a very big model with very small cell sizes, small groups, a lot of different predictors and things like that. But maximum likelihood is what I would generally recommend when it works. Maximum likelihood is important when comparing different models. So if we were selecting, eventually we'll go into linear regression, and so we'll have groups, we'll have other variables, and we'll try to adjust for a number of things in addition to just being in groups. And then the maximum likelihood makes more sense for testing between different groups. So that's what I would recommend. Results in these type of one-way examples, I don't think will change all that much. You'll get slight changes in numbers, but pretty much they'll be quite similar. And that's really just a computational issue, right? And so what this one does, and you can summarize that, it gives some different statistics for comparing the fit. There's some these couple things are called information criteria. Eventually we'll talk about what those are in the context of linear regression. There's a log likelihood, likelihood methodology, and deviance is -2, the log likelihood. A little bit about residuals. They're part of the diagnostics of the fit. Well, you can use that more with linear regression. And then it gives us a couple things here, random effects, right? So it estimates the variances among the diets, the diet averages, and it estimates the variance within the groups. So this is our sigma squared, my copy, printout copy. This is here. So in this example, diets, right, so you have sigma squared among the diet effect as 38.38. The square root of that is the 6.195, and this thing, so that's, put a little hat on that if you want to as an estimate. The residual there is 44.60, and sigma hat on this one is 6.678. Quite similar. They wouldn't necessarily have to be. So our estimate of our interclass correlation for this one, the estimate of this one over the 38.38 over that plus the 44.60 is, I calculated that and put that in there. Yeah, next page, yeah, 0.46, right? So about 46% of the variability of the overall, the variance of a measurement is due to the groups, which in this case are diets. So that's pretty big. The diets are really making quite a big impact on this one. So that's one thing that comes out of this. That wouldn't be there in the fixed effects. Would be the same type of estimation. But that's that first part there. It also does an estimate for the overall mean and the standard error. So what is mu? There's just an overall fixed effect, which is the population average. So this is just an estimate of mu with a standard error. It's testing whether there's a zero, it's zero, which we're not too interested in because we know that the lifetime's not going to be zero. But you could use that to make a confidence interval. We have that. There is a second package, LMER test. The people who made the LME4 package don't like p-values, don't like hypothesis testing, so they don't automatically give it to you. I think they're quibbling about a few technicalities, but they, I don't know, they didn't put it in their package. So there's another package called the LMER test, and some other ones that are out there that people have written that will give p-values and tests. And so within that, there's a random effects NOVA that does a test. It is actually using something called a likelihood ratio test, and it gives a p-value that's very, very small. And so the result of this test means that the variance is not zero, right? Which means that there is a difference in groups. So it basically corresponds to the qualitative conclusion from the first ANOVA test that these groups are significantly different. Right? But then there's functionality in here for confidence intervals. You get confidence intervals for this is the sigma 1 here is the mean, the confidence, the sigma 0, sigma squared alpha. So this is for sigma, I can't write on here, right? So the confidence interval, there's that one on the page. Right. There it is. So in reading this is going to be the confidence interval for sigma alpha, or sigma squared, yeah, sigma alpha. And this one will be the sigma epsilon. And this will be a confidence interval for the overall average. So this gives us confidence intervals for sigma alpha, sigma epsilon, and mu, and it reports them as 3.78 up to 12.52. This one is in 6.21 up to 7.21, so it was more precise. And the intercept at 32.4 up to 44.3 for their overall mean. So you could look at those different things. Right? And particularly this one is far away from 0, and there would be some non-trivial variation. It would be significant. There's other functionality that's in there, and so if you get into a case where you want to fit one of these models and pull off, look at the different aspects of things, you can look at the coefficients. These become the estimates of mu sub I, mu plus an epsilon I. You get estimates of those. They're almost like the means by group, but they're not quite the same, right? Because there's this maximum likelihood fitting. It views the alphas as a sample from a normal, so they get kind of adjusted a little bit. And in fact, I think they get pulled up more towards the center. So the low ones, I don't know, this one's pulled up higher. No, these are the ones here. These get pulled in toward the center a little bit, right? By the effect of this model. It gets shrunk in a little bit. Overall, just the raw means, right? The raw means have variability within the groups, but the normal distributions as things should be for the effects, kind of not too spread out. So the small ones here gets pulled up a little bit. This is kind of a large mean. It gets pulled down. This one is about the same. This small one, estimate by the direct mean estimate, gets pulled up a little bit. This one gets pulled down just a little bit, and that one is not too much different. So they kind of put all the data together can help estimate the average within a group. So this is something, so within random effects, the estimate of mu sub I, which is mu plus alpha I, is pulled toward the center. This effect is called shrinkage, right? And it actually can be viewed as a very desirable thing. So the means that happen to be the most extreme don't get estimated out there so far. They're likely different, but there's a good chance that the ones that are the most extreme, just by chance, happen to get small observations in their sample. And the ones that are the largest just happen to get a few extra bigger observations, so they might be pulled away a little bit. This kind of conservative, this shrinkage towards the middle. So it differs from just the average in that group a little bit in the sense that they get pulled away. And it's a small effect near the middle of the data, but the groups that are more extreme get pulled in, and that can have some desirable properties in terms of mean square error in the sense that they, right. Anyway, you see it slightly differently there in that. You also can look at the estimates of the alpha i's. These, the random effect parts, these things here are the alpha I hats. Estimate of alpha I is pulled toward 0. This is again, essentially the same shrinkage, but just looking at that one. And so the estimate will differ slightly from if you took the y bar I minus the overall average. Right? If you just took the sample data in that group minus the overall average, it would be a little bit more extreme than the estimate of that alpha I under this random effects model. Which again is just a fact of life that this under that normal model that it's centered at 0, it doesn't like to have things out there and produces something under the model, under the likelihood that says it's fairly normal that's kind of shrunk towards 0. So you can pull those things off. See that this deviation here, you just take the mean by group and then subtract the overall mean, it would be -6. But this one says the estimate of alpha is not quite that extreme, -5. So it's pulling it towards 0 like that. So a few things like that happen in this. You can extract a few more details in certain ways. And so the upshot of this is that we get some information about these different variance components. We get our overall test, F-test as before. And so within that kind of enhanced model, you get a little more information. Some things look just a little bit different, but not too terribly different. But any questions? So this is kind of a kind of introduction overview to this. There's obviously more details in figuring out these distributions and figuring out how this works. But it's something you might see, and we'll see a little bit more as we go along. Right? So what happens with the judges? Right? When we did our analysis of variance, we got a very significant result. If you do the LMER, the random effects one, it would be specified like that, the percent, as a function of random intercepts. This one typically means intercept, and given judges, it's random within judges. That's how that coding is presented. And so we'll get an estimate of the variance here and the variance of the residuals. Again, a pretty large value of the interclass correlation coefficient, right? So 31.5 over the sum of these two things. Still, it's looking like 40% of the variability by the judges. That's pretty large in this case, right? The fixed effects, this is the estimate of the average percentage, confidence intervals for these different things. And anyway, that's just how the output would look in this case. A confidence interval for the mean, confidence interval for sigma alpha, and so on. Right? I didn't go through all the calculation to get a confidence interval for the interclass correlations. Anyway, I just didn't get around to it. So you could do it if we were interested in it. And I plan to look a little bit more at packages. So the things change from year to year with these different packages. That's one some statistical package computer programs like SAS, right, have a long review period, and they only allow things to come out in the software that's official. Right? There's an official group that certifies everything that comes out. Right? In the main commands. R with its packages is a little bit different. The different authors can do things and publish it, and so things can kind of change a little more rapidly, which is good. But it also means that some things that you were doing before no longer are there, and so. But we'll figure out how to do some of these other things before too long. Right? So what I wanted to do a little bit more is talk about when to use some of these random things. So there is the handout here, right, that has some examples on there. So random or fixed effects. These are from a book by the authors are Nieder, Kuttner, Nacht, Kuttner, Nachtsheim, and Wasserman. It's a large book on applied linear and nonlinear models, and that has details on this. Linear, and I think nonlinear. But these combination of authors with some others have had several different textbooks that different topics around these. Right? And so, say in this first example, the 16.14 example again. question we're asking, should we view the groups as random? In which case we'd use the random effects analysis of variance to estimate variance components and things like that, and report that interclass correlation. Or are we really interested in the groups that are presented there? In which case we wouldn't need to do anything like that, right? So why don't you read the first one? So does it appear that these machines are a random sample from some population, or probably fixed, yeah. Do others agree? Does that make sense that it would be fixed effects for these machines, right? So it's totally, in some other reality, it'd be totally plausible that these were 6 machines out of, thousands, in which case it'd be a random sample for this. But this person has 6 machines and is interested in those 6, right? So 6 specific machines. So I don't see any reason to use random effects here. For this one, because it's interested in those 6, even though it's very you could easily imagine a much larger company or with maybe several different buildings and so on that would have many machines, and you test 6 of them. That would be random, but we want to know which one of these 6 is different, right? So more fixed, right? 16.15 is a soft drink distribution, and there are 5 agents. Let's look at this one. What does somebody else suggest? Should we random effects, fixed effects? Yeah.
I think fixed effects, and it's a pretty similar style to the first one. It's those 5 agents.
How would this problem possibly be phrased if it was going to be random effects, do you think?
They picked like a couple agents randomly from maybe all software distribution, something like that. So just these specific
Yeah. So I wonder if they're trying to emphasize something that this is kind of the premium distribution. You have your top 5 that deal with certain things. So there's only 5 of them. Which one of them are doing the job more timely? Does somebody particularly stand out, right? If somebody's standing out on the top, they're very timely, short times, I guess. That's good, so maybe they'll get a reward. But if somebody's really long compared to the other one, maybe they're going to be demoted. So they want some statistical evidence to compare performance, right? If there were 100 agents that did distribution of all their other products, and they wanted to audit orders from 5 of selected from the 100, then it's more a random effect, right? You want to get more at the, is there variability among these, or what's really the magnitude of variability, right? And what percent of the variability is due to agents. If the percent of variability due to agents is 1 to 2%, that's almost nothing, and they're doing quite similar. But if 40, 50, 60% of the variability is due to agents, then it would really justify doing something about how agents perform or trained or something like that. Right? So this one, again, yeah, primarily fixed. Maybe the premium is meant to suggest that it's a special agent, so you're really interested in those. 24.9, coil winding machines. You get examples with just so much variety, and some things could be very interesting to an engineer or something. Some people working in certain areas, and others that not necessarily. So coil winding machines, not necessarily my most exciting topic, but it's a perfectly good application. So with this one, seem to be random effects or fixed effects.
Random.
Yeah, right. So this one looks random. Random effects for machines. Like many, choose 4 machines, 10 measurements on each machine. Right. You're not necessarily interested in those particular machines, but where is the variability? Is it variability across machines or within one machine? Could it be re-engineered to reduce variability? And what should you affect? Should you tune the machines that are kind of out of whack, or I don't know? Where should you concentrate your efforts? And how about the sodium content? 24.7. So the sodium content of beer, lager beer. Yes.
Random.
Yeah. And what do you read in there that suggests that?
The random 6 brands from a large number of brands, and then they chose 8 12-ounce cans at random from different outlets.
Mm-hmm. Yep. So they're interested in the 6 brands out of many. They're not necessarily interested in those, but is there variability? How much variability is there across brands? But you have to kind of account for some of the variability within individual cans and things like that. So I may be interested in knowing that if those 8 cans were all taken from 8 establishments, then you really would have a little more structure. You would have 6 brands and 12 establishments, and then 1 can from each one. So eventually we'll get into a 2-way analysis of variance. And that would be a design that would create a bit of a problem, because we'd only have 1 observation per combination of brand by location. And so essentially you have an N of 1 in each of those crosses. And that will create, have to be 2-way ANOVA in a certain way. So on the back there are some others that are kind of in the chapter between these two. The first one we're in this chapter 16, which is the fixed effects 1-way ANOVA, and the chapter 24, which had random effects, and the 18 somewhere in the middle. So let's take one of these, 18.15, helicopter service. What is this?
Safe effects.
Fixed, yeah. Which part is it fixed for?
Time periods, the groups, and their costs, and specifically chosen
Yep, yeah. So the time periods are specifically chosen, so you're interested in those 4. There's no other time periods that it can be studied. So that's definitely fixed. It has this kind of interesting thing that it's 20 days over time. So it's this kind of time series pattern. So, you might do with this random effects ANOVA, but you might put in something like weekday, weekend, day of the week, or maybe some type of time structure. Eventually, we'll do something like that. Right? In the linear regression ANOVA, you could put something like day of the week in here plus that random effect. So there's kind of a random effect of time period, or it'd be fixed effects. We wouldn't really be doing that in that case. But you can put extra variables in here and put things like time effect. So this one's kind of interesting that, again, you have to kind of wonder about it fully. Is it really doing everything that's in there? Right? The other 2 really are fixed effects as well, just to give it away. In the winding speeds, there's slow, normal, fast, and maximum. So there's 4 levels, and they're interested in those 4 levels rather than a random level. And the other one, they're interested in sales, production, and research and development division. So there's 3 divisions. So they're interested in those rather than random divisions. If a huge telecommunications company was divided into service units of some sort, and you had thousands of service units, and you picked random service units and investigated those, then you could make it a story where it would be random as well. So a lot of things can be viewed as one versus other. Sometimes it stands out. Sometimes it's a little bit fuzzier what you're doing here. So, but anyway, it's random effects as we go through other applications. We'll see it coming back again. That's a little bit more detailed than in the book about that one. Okay. So, have a good day.
Yeah, I know. He doesn't just him talking. Yes, it looks like.
Today I don't. I have office hours tomorrow. What's it going to look like tomorrow? So tomorrow I think it's 11:30 till I'll probably be around till about 3 or something. Probably 3:30, something like that tomorrow. Can you stop by sometime tomorrow? Okay. Talk to you then.